Section 12.10 deals with oxidation of alcohols. And before we get into the nuts and bolts of it, let's compare oxidation and reduction. And you probably remember in the video where I went over oxidation numbers for carbon that I mentioned that oxidation was gaining bonds to oxygen and losing hydrogens. And you can clearly see here that we lose 2 hydrogens going from this secondary alcohol to acetone. And you also probably remember me saying that reduction was gaining hydrogens or losing oxygens. Well, we don't lose any oxygens, but when we do the reduction, we gain 2 hydrogens going in this direction. Another thing you could do is to calculate the oxidation number of the carbons. So here we have a carbon surrounded by 1, 2, 3, 4 electrons, and so the oxidation number of this carbon is 0. And here we have a carbon that is surrounded by 1, 2 electrons, and so its oxidation number is +2. And since we're going from 0 to +2, going from the alcohol to the ketone, oxidation is losing electrons, and therefore this is oxidation. Okay, well, if you oxidize a primary alcohol, the thing is that a primary alcohol will first be oxidized to an aldehyde, followed by oxidation of the aldehyde even further to make a carboxylic acid. Whereas when you oxidize a secondary alcohol, it produces a ketone, and then it will not be oxidized any further. There is one exception to this that we're going to see much later in the course, but you don't need to worry about it at all for the next quiz, for quiz 12. For a tertiary alcohol, and this is something that I brought up earlier on in the class, a tertiary alcohol cannot be oxidized under any circumstances. It will never undergo oxidation. And the reason why a primary and a secondary alcohol can undergo oxidation and a tertiary can't is because a tertiary alcohol has no protons on the alpha carbon. You see that we only have R groups attached to the alpha carbon, whereas if you look at a primary alcohol, it has 2 hydrogens attached to the alpha carbon, and a secondary alcohol has 1. So again, I repeat that when you have 0 hydrogens attached to the alpha carbon, oxidation will not occur. Now let's take a look at one of the oldest ways of oxidizing an alcohol is to use chromic acid. And I'm sure you all remember from general chemistry that H2SO4 is sulfuric acid. Well, if you replace the sulfur with a chromium, you get H2CrO4, and this is called chromic acid. Its Lewis structure is shown right here. It's the same Lewis structure as sulfuric acid. You just replace the sulfur with a chromium. And the oxidation number of the chromium in chromic acid is +6. And chromic acid is actually made in the laboratory. And there's a couple of ways that you can make it. One of the ways is to take chromium trioxide, so CrO3, and combine it with H3O plus and acetone. And so all of this together would be CrO3, H3O plus, and acetone. And that will produce chromic acid. Or another way is to combine sodium dichromate, which is Na2Cr2O7, with sulfuric acid in water, and that will also make chromic acid. So again, whether you're combining chromium trioxide, acid, and acetone, or sodium dichromate, sulfuric acid, and water, either way, you're making chromic acid. And sometimes we refer to this as the Jones oxidation. So Jones oxidation. If you look it up on Wikipedia or something, I'm sure they'll have an entry about Jones oxidation. Anyhow, let's move on. If we take a look at the mechanism, in the first step, what happens is that the alcohol combines with the chromic acid to make what's called a chromate ester. And then the chromate ester undergoes an elimination reaction to form the double bond between the carbon and the oxygen. You do not need to know this mechanism. I should say it might be, or how would I put it? It's something I will not ask, okay? I'll put here, will not ask mechanism. However, something that I haven't said yet in this class, but I would have told you this in Organic Chemistry 1, if you think about any class that you've ever enjoyed in high school, university, anywhere, it's always something that you understand. And so if you want to take a look at this mechanism and get to know it, it will definitely help you moving forward. So this is oxidation with chromic acid. Well, what happens with a primary alcohol is that the primary alcohol will get oxidized to a carboxylic acid with chromic acid. However, it's kind of like a runaway train, and it just keeps going all the way to a carboxylic acid. And that begs the question, is there a way we can oxidize a primary alcohol and stop at the aldehyde? Can we just get it to stop here? And the answer is yes. We can do that using a reagent called pyridinium chlorochromate, or PCC for short. Here's the structure of pyridinium chlorochromate. My students never bring up the Lewis structure or anything of pyridinium chlorochromate. However, they all know that the acronym PCC, if you combine that with your alcohol and dichloromethane as a solvent, the primary alcohol will be oxidized at an aldehyde and it will stop right there. Reaction is complete. So very cool reaction. And the reason why I like the PCC reagent is it's just a solid compound. It's a kind of an orangey red solid. You mass it out on the balance, you throw it in the reaction mixture, you let it stir, and you collect your aldehyde. Very straightforward chemistry. Now, whether you either are using chromic acid or PCC with a secondary alcohol, either way, you're going to get the same thing. Since a secondary alcohol can't be oxidized past the ketone, it doesn't matter if you're using this super strong oxidizing agent or if you're using PCC, which is much more mild, you're still going to take that secondary alcohol and convert it to a ketone. The only time you would, or something you would want to take into consideration here, though, is that since chromic acid is so strong, it might oxidize something else in the molecule. So maybe you might just want to go with PCC because it's a lot milder reagent. What else do we have besides chromic acid? It says here that chromium reagents, like chromic acid, are toxic and horrible for the environment. And thus, organic chemists are always looking for a new way to oxidize an alcohol, something that's less toxic and more environmentally friendly. There's a couple of them that we're going to look at right now. The first one is the Swern oxidation, and the second one is called the Des-Martin periodinate. Let's start off with the Swern oxidation. And the Swern oxidation is actually a two-step reaction. In the first step of the Swern, so I'll just abbreviate it here. So the Swern, the first step, you take COCl2 in brackets and combine that with DMSO, which is dimethyl sulfoxide. And in the second step, you treat it with triethylamine. So the COCl2, that's called oxalyl chloride. So again, that's COCl, and the whole thing is in brackets. And then dimethyl sulfoxide is DMSO. And when you combine the alcohol, the COCl2, and the DMSO, it ends up making this really interesting sulfonium ion, this chlorodimethyl sulfonium ion, and that is the active oxidant. You can see you also end up producing carbon monoxide and carbon dioxide. You do not need to know this mechanism. I will not ask it. So will not ask mechanism. But then once you form that active oxidant, the active oxidant reacts with the alcohol, and then the triethylamine comes along and does a deprotonation, a second proton transfer, and then we end up doing an elimination to form a ketone, and we also form dimethyl sulfide, which is a stinky compound. And thus, if you ever do a Swern oxidation in a lab, people will always know because This is so smelly that anybody will be able to detect it with their nose very easily. Not only will a Swern oxidize a primary alcohol to an aldehyde, it will oxidize a secondary alcohol to a ketone. So the Swern will take a primary alcohol and convert it to an aldehyde, and it'll take a secondary alcohol and convert it to a ketone. All right, well, like PCC, the Swern oxidation will convert that primary alcohol to an aldehyde, and again, the secondary alcohol to a ketone. Very useful chemistry. Again, those chromium reagents are toxic and horrible for the environment. So besides the Swern, which is kind of stinky, what other options do we have? Well, we also have what's called the Des-Martin periodinane. And this is the structure of the periodinane right here. You can see it's got 3 acetyl groups on it. If you've ever studied acetyl coenzyme A, this is an acetyl group here. That's what the AC stands for. But here's our Des-Martin periodinane. You don't need to memorize the structure. In the mechanism, I've never asked the mechanism to a student, but the Des-Martin periodinane is not as stinky, and not smelly at all, as a matter of fact, and it does the same chemistry as the Swern oxidation. It'll oxidize a primary alcohol to an aldehyde and a secondary alcohol to a ketone. The Des-Martin periodinane is used in CH2Cl2 dichloromethane, the same way PCC was. Now, if you're wondering about the mechanism of the oxidation using the Des-Martin periodinane, it's shown right here. You can see it's kind of a rearrangement, if you will. This is another mechanism that I will not ask. So we'll put here, will not ask those curved arrows. But here we go. And if you're wondering, what other advantages does the Des-Martin periodinane have? Another advantage that it has is that it's not acidic. So if you have anything that's acid labile in your compound, it's not going to be degraded. And it doesn't require high temperatures. The only caveat to the periodinane is that it's shock sensitive, so it's slightly explosive, so I guess you have to handle it with care. It's a neat question here. You've got a whole bunch of interesting things here. You've got a secondary alcohol. You got a primary alcohol, and you have an aldehyde. And you're treating it with chromic acid. Chromic acid. Well, we said that chromic acid would oxidize an aldehyde or a primary alcohol to a carboxylic acid. And we said that it's going to oxidize a secondary alcohol to a ketone. And that's exactly what would happen. You oxidize all 3 functional groups, and you end up producing 2 carboxylic acids and 1 ketone. Kind of a neat reaction, though, oxidizing 2 different functional groups, but 3 functional groups at once. Okay, with all that information in mind, let's take a look at some reactions and see if we can draw some products. The first one is a reaction of cyclopentanol with sodium dichromate, sulfuric acid, and water. So again, this is nothing more than a way to make chromic acid, H2CrO4, and that is going to oxidize that secondary alcohol to a ketone. Let's draw out the ketone. This is called cyclopentanone. Here we go. The next one, we're taking a primary alcohol, primary and we're using the same strong reducing or oxidizing agent. And so we're going to convert that alcohol into not an aldehyde, but a carboxylic acid. So we'll write carbon here, and then we're going to oxidize that all the way to a carboxylic acid. The next one is a Swern reaction. So this is the Swern oxidation. First step is dimethyl sulfoxide and oxalochloride. The second step is triethylamine, and that's going to oxidize the primary alcohol not to a carboxylic acid, but to an aldehyde. So let's draw the structure of that aldehyde, which would look like this. And then in the last one, we have a primary alcohol here, an aldehyde here. Well, desmartin periodinane, DMP, and dichloromethane will oxidize the alcohol, but not an aldehyde. And thus, we are going to only oxidize left-hand side here. And we're going to end up with this trans dialdehyde. So, and there we go. That's it. We're going to skip section 12.11, which deals with biological redox reactions. So it talks about nicotinamide, adenine, what was I talking about? So it talks about NADH and NAD+, and I'm sure you've covered these compounds in biology when you talk about the Krebs cycle. So it talks about how it's reduced, and it talks about the oxidized form. So I'm going to skip all that right now. What else? I'm going to skip the section, this part about phenol. We don't cover any of that. And yeah, so don't worry about sections 12.11 so we're going to, again, ignore or skip, 12.11 and 12.12. Don't worry about those. They're not going to show up on the quiz. Let me go back here. Where am I here? And that brings us to the last section of chapter 12. Just like chapter 11 and chapter 9, chapter 10, chapter 8, chapter 7. And the last part of all these chapters just deals with synthesis. It's nothing more than getting practice in all the reactions that you've learned so far. These are all things that we learned in Organic Chemistry 1. And in this chapter, we learned about oxidation using PCC or chromic acid. We learned about reduction using lithium aluminum hydride, sodium borohydride, hydrogenation. We learned about oxidation numbers. And here you go. These are some of the reactions that you know now. I mean, what are the ones that you would have covered in this chapter? We covered the reduction reactions. We covered the oxidation reactions. Some new stuff also would be thionyl chloride, phosphorus tribromide, and then Grignard chemistry, which, where is my green chemistry? I guess it's not on this slide, but we also covered Grignard chemistry, which is here. So we talked about Grignard reagents reacting with a ketone or an aldehyde and how they only add one equivalent. Whereas if you react a Grignard with an ester, it adds two equivalents to make a tertiary alcohol. And then it says here, there's no one reaction that converts an aldehyde into a ketone. However, with a Grignard, you can convert an aldehyde into an alcohol and then oxidize that to a ketone. So that's something that's kind of neat, shown right here. You can see we're starting out with an aldehyde. We treat it with a Grignard to make an alcohol. Then we oxidize the alcohol to a ketone. So that's something kind of new. And with all that information in mind, let's try some practice problems. So let's see here. We'll start out with A. Let me see. Just give me a second. I'll give you a second to start looking at the first one. Just going to do something here. Okay, so I'm going to work it here just to make sure I have enough room. We are going to begin with 12. So this is 12.24A. So we've got a terminal alkyne here, 1, 2, 3, and we want to take this and we want to make a primary alcohol. Well, the good news is we only know one way to make a primary alcohol without changing the number of carbons here, if we had the alkene, right, if we had this alkene, then we could just do an anti-Markovnikov addition of water using borane and THF, followed by hydrogen peroxide and sodium hydroxide. And so to reduce that alkyne to an alkene, since it's terminal, we can't use sodium metal reduction. The only thing that you're supposed to use, or the only thing you can use, is hydrogen in Lindlar's catalyst, which will give you the alkene, which looks like this. And then to convert that into the primary alcohol, we're first going to treat that with borane and THF, followed by H2O2 and sodium hydroxide. All right, let's move on to, you know what, there's another way to solve this one too. Did anybody think of another way to solve this? I just noticed another way. And you could use some of the chemistry that we learned in this chapter, actually. This is using, you know, the stuff that we learned in chapter 11, but did anybody see another way to make this compound? Using reduction? And reduction of a carbonyl, I mean. Could anybody tell me what the first step of anti-Markovnikov water across the triple bond is? Like if I took this compound, I've got the triple bond here, and I wanted to make this compound, where I do anti-Markovnikov of water across the triple bond. I don't know if I can't see if you're writing in the chat or not, but could anybody unmute their mic and tell me a way to do that? Okay. Anybody there?
Yeah, I can hear you, but I don't know.
Okay. Unsure? Okay, so for this one, you'd want to use a hindered borane, right? Something like 9 bbn. So you would do 9 bbn and then hydrogen peroxide and sodium hydroxide, which would give you this compound. But that compound is going to undergo tautomerization. So tautomerization to give you the aldehyde. Right? You end up with this aldehyde like this, okay? And then to convert that into the alcohol, so you want to convert that into 1, 2 carbons and the alcohol, you could just use sodium borohydride. I mean, you could also use lithium aluminum hydride, but let's just pick this. You could use sodium borohydride and methanol. That would work too. Either strategy is perfectly reasonable, I would say. They're the same number of steps. So yeah, 2 possible strategies to do that one. Let's skip B. Let's try C since it involves oxidation. So this is question 12.24C. We're trying to take 1-butene and we want to convert that to an aldehyde. This is called butyraldehyde. And here we have 4 carbons and here we have 4 carbons. So we're not changing the number of carbons. And we know that we could make an aldehyde if we had the primary alcohol, right? If we had this alcohol, all we'd have to do is oxidize that using PCC, going back this way, and that would give you the aldehyde. So the question then becomes, how do I get from the alkene to the alcohol? Well, all I need to do is an anti-Markovnikov addition of water across that double bond. So the first step, I'm going to treat that with THF, sorry, Mr. Dion is tired, so borane and THF, followed by hydrogen peroxide and sodium hydroxide, like that, and that's going to give you this compound, and then all we got to do is treat that with PCC, or you could do the Swern, or you could do the Des-Merten periodinane. They will all oxidize that primary alcohol to a ketone. There you go. So that's kind of a fun one. And then, yeah, why don't we move on to another question? Let's try something that involves some Grignard chemistry. So let's move on to question 12.26. And the first one shows this aldehyde. So this aldehyde, so we have a total of 6, 7, 8 carbons in the molecule, and we want to convert it to a compound that has 10 carbons. So we're going to have 6 in this ring, 7, 8, 9, 10, and we have a carbonyl. So you can see that we're adding these 2 carbons, and where are those 2 carbons going to come from? Well, we could add them using an ethyl Grignard, right? If we just take, in the first step, ethyl magnesium bromide, followed by treatment with aqueous acid, that is going to add those 2 carbons. And now, instead of having an aldehyde, I'm going to have an alcohol, but I've added the 2 carbons from the ethyl group. Now, if I want to take that alcohol and I want to oxidize it to a ketone, I have a whole holy host of options. I could do sodium dichromate, sulfuric acid in water, or you could use chromium trioxide, H3O plus in acetone, or you could use Des-Martin periodinane, or you could do a Swern, which is the first step, treating the compound with dimethyl sulfoxide and oxalyl chloride, followed by triethylamine, or what's the other one that we learned that it's escaping me at the moment? So we use Swern, Des-Martin. Yeah, I guess that's it. Yeah. Oh, PCC. Yeah, PCC. There we go. So a whole holy host of ideas to oxidize that. Let's try another one that involves a Grignard. So I'm going to ask my students about this one. Let me use the blue pen. So this is B. We're starting with this aldehyde, and I want to convert it to this ketone. Like that. How many carbons am I adding here? Can anybody tell me?
One.
Yeah, just 1 carbon. Exactly. Thanks, Lindsay. Great. So if I only need to add 1 carbon, then I know that I'm going to use methyl magnesium bromide, or you could put methyl magnesium chloride. That's fine too. And I already have my aldehyde. And thus, all I need to do is take that aldehyde and treat it in the first step with methyl magnesium bromide, and then in the second step with H3O plus, and that gives me this compound here. So I end up with a secondary alcohol, and then I want to oxidize that to a ketone, and thus I could use any one of these ways of oxidizing. So I'll just copy them all. Copy, paste it right here. So paste. There we go. We'll even change the color. There you go. Oops, I didn't mean to do that. Let's see. There we go. All right, so any one of those oxidation methods would work. So a little practice on Grignard chemistry. Okay, so why don't we do a few more problems and then we'll call it a day for chapter 12. And what I'd like to take a look at are I'd like to look at 2 problems. And let's see here. These are ones that are not in the textbook, but I think they're really good. So this first one is where we have to add some carbons. So I want to try this one. And I'd also like to try, I think this one is a doozy. So I like this problem. You start it with a secondary alcohol and you convert that into a ketone like that. Okay. So I'm going to give you a second to write those problems down. Then I'm going to stop recording. I'll give you 10 minutes to work on both of those problems, and then we'll come back and we'll solve both of them, and then we'll call it a day. So these are the last two problems that we'll look at. Now, before we, sign off here and give you a chance to try them, keep in mind that in the first compound, you've got 5 carbons. Then you've got 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6. So we go from 5 carbons to 6 carbons. And then in the second one, we're starting it with 3. We're also starting it with 5 carbons and 1, 2, 3, 4. We're also ending up with 6 carbons. So something kind of similar in both of them, but similar, but there's some differences here too. So I'll give you a few minutes to think about that, and we'll call it a day after that.